Hi everyone, my name is Samar Sinha, and today I will be talking about our work on test time self-training under distribution shift. This work was done alongside Peter Geller, Francesco Locatello, and Bernd Schiele. When training neural networks, it is impossible to train the model on the exact distribution that the model will be evaluated on. Models need to be able to generalize to novel test distributions, such as going from training in simulation to real natural images, as we can see here. Models may also have to generalize to different scene semantics, such as being evaluated in a different city. Here we can see that the model is being trained on data from Switzerland while being tested on data from California. Similarly, here we see the model has to adapt to different weather conditions, such as foggy surroundings, extreme rain and snow, or nighttime. Learning models that can generalize to different test distributions is key to deploying neural networks. Towards this, in this paper, we explored the question of how we can refine a model trained on a large dataset to a different data distribution without requiring label information for the testing data. There exist a variety of solutions that explore the same problem. More classical approaches, such as zero-shot domain adaptation, don't require labels for the novel data distribution. However, they require changes in the training protocol itself. More recent methods perform few-shot transfer learning to the novel data distribution. However, such methods require label information for the novel data. Similarly, model patching is able to generalize to multiple tasks at test time, but also requires labels for each support task. In contrast to other techniques, our method, test time self-training, or TeST for short, does not require any adjustments to the training of the model, or labeled information at test time. TeST is also extremely data efficient as it works with as few as 64 unlabeled images. TeST fine-tuning happens in two distinct stages. First, the model is copied to a teacher and a student network. The teacher is trained to learn invariant representations from the data by performing consistency regularization in the learned embeddings between a strong and a weak augmentation of the same image. After training the teacher, the student is then trained using knowledge distillation from the teacher to learn robust representations from the data by minimizing the divergence between the teacher and the student predictions on the task. An entropy minimization term is further added to the student predictions to learn confident predictions. We thoroughly evaluate the model's performance on a challenging set of autonomous driving object detection datasets using a trained deformable detection transformer model. Here we see the performance of TeST compared to other baselines on 4 challenging benchmarks. We can see that TeST is able to significantly outperform all baselines and gets comparable performance to classical domain adaptation methods, which require 5 to 10 times more data. Similarly, we test the model using a different object detection architecture, namely a faster RCNN. We see that a similar trend holds for faster RCNN as well. We further evaluate the model on the pixel-wise semantic segmentation task on autonomous driving datasets. We again clearly see that our method significantly outperforms all baselines. We also show qualitative results before and after fine-tuning using TeST. We can clearly see that the model is able to significantly improve on its predictions by getting rid of false predictions and increase the number of correct labels. Here are some more qualitative results before and after TeST was applied. Finally, we evaluate the learned embeddings after TeST was applied on the models by qualitatively analyzing the 3 nearest neighbors in the learned embedding space. We can see here that the model learns an interpretable embedding after training. Thank you for your time, and please check out our paper for full details.